In this video, we're going to take a look at some of the considerations that need to be taken into account when you're projecting raster data in the ArcGIS environment. We're going to work with two different types of raster data for this example. The first is a WorldView 2 satellite image. The second is a high-resolution land cover dataset that was derived from that WorldView 2 satellite image. The WorldView 2 image is what we would call continuous data. In a continuous raster, the pixel values have meaning relative to one another. For example, a pixel with a brightness value of 100 is brighter than a pixel with a brightness value of 80. Our land cover dataset is a discrete or thematic raster. In this particular case, land cover class 1 means tree canopy and land cover class 4 means water. This doesn't mean water is 4 times greater than tree canopy. They're simply discrete classes used to describe the individual land cover values. Projecting raster data is the process of transforming a raster data set from one coordinate system to another. You do this within ArcToolbox, under Data Management Tools, Projections and Transformations, under the Raster toolset and the Project Raster tool. It's important to note that the approach to projecting a raster dataset will differ depending on if you have a discrete raster dataset or if you have a continuous raster dataset. And what you really need to pay attention to is your resampling technique. In this video, what I've done is I've used several different resampling techniques to project both the land cover and the WorldView 2 image to new rasters. So let's take a look at how the Project Raster tool works. The first step is to define your input raster dataset. You'll then define the output raster dataset using .tif or .img if you want it in GeoTIFF or Imagine format respectively. You'll then define the output coordinate system, which is the coordinate system you want it to be transformed to. You'll apply a geographic transformation if necessary. Then you'll select the resampling techniques and the output cell size. Typically, the output cell size should be the same as your input raster, and that's what it defaults to. Under your resampling techniques, you have 4 choices with ArcGIS: nearest neighbor, bilinear interpolation, cubic convolution, and majority resampling. The general rule is that for discrete raster datasets, you'll want to use either nearest neighbor or majority resampling techniques. If you're using continuous data, particular imagery, you have a choice between nearest neighbor and cubic convolution. If you're interested in maintaining the spectral integrity of your imagery, you'll want to use nearest neighbor. However, if the spatial arrangement of pixels is very important, you'll want to use cubic convolution. For the WorldView 2 image, I've projected the original image, which was in a state plane coordinate system, to a UTM coordinate system, and I've done that twice. First, using the cubic convolution resampling method, and then using the nearest neighbor resampling method. Now we'll use the swipe tool from the effects toolbar to compare the results of the reprojection, first using the cubic convolution resampling method, and then using the nearest neighbor resampling method. So in using the swipe toolbar here, I'm swiping away the original WorldView 2 image to reveal the cubic convolution image. Now you'll notice there are some minor changes in the pixel values, but overall the spatial arrangement of the pixels has been maintained, which is to say that we still have very nice straight lines. If we turn off the cubic convolution image and turn on the nearest neighbor resampled image, we see that the lines now appear jagged, particularly in the north-south direction. Now the nearest neighbor technique is much quicker. During the reprojection process, it simply finds the nearest cell and it assigns the new raster the value from that cell. In cubic convolution, it uses a weighted average of the surrounding 16 cells. So nearest neighbor is quicker and it's going to preserve those spectral values. But in the case of this high-resolution WorldView 2 image, cubic convolution looks to be a better choice because it preserves the spatial arrangement of features. Now we'll switch gears and take a look at the land cover output. For the land cover dataset, I've taken the original land cover, which was also in a state plane coordinate system, and projected it to a UTM coordinate system using 3 different resampling techniques. The first is nearest neighbor, the second is majority, and the third is cubic convolution. Once again, I'm going to use the swipe tool from the effects toolbar to swipe away the original land cover image to reveal the resampled ones below. First, we're going to swipe away the original land cover to reveal the nearest neighbor image. As we swipe back and forth, we can see that there's some minor changes in the pixel values and that we've altered the shape of features. We see somewhat similar results if we turn off the nearest neighbor and turn on the majority. So once again, we're swiping away the original land cover to reveal the new majority filtered land cover. One might argue the majority filtered land cover looks a little bit better because it doesn't create so many jagged edges. In both cases, the nearest neighbor and the majority land cover datasets have the exact same pixel values as the original land cover. Now let's see what happens when we use a cubic convolution resampling method. The first thing that you'll notice is that we have another pixel value, 8, that we didn't have in the original land cover dataset. This is because the cubic convolution method takes an average of the surrounding pixel values. As a result, it's creating new pixel values that didn't exist in the original image. This can introduce a multitude of errors when you're working with thematic datasets. By using our swipe tool to remove the original land cover and expose the cubic convolution land cover dataset, we see the effects of that cubic convolution filter. We have all these nasty edge effects, and we have this new land cover class 8, that didn't exist in the original. The bottom line is that whenever you're reprojecting raster data that's of a thematic format, you want to use either nearest neighbor or majority. Cubic convolution is going to change your pixel values and is highly unsuitable. Reprojecting raster data is easy to do within ArcGIS. However, you have to understand that anytime you project your raster dataset, you're creating a new raster, and no matter what resampling technique you use, you fundamentally alter the pixel values. It's very important to select your resampling technique correctly, particularly when using thematic or discrete data, as cubic convolution distorts the pixel values. When working with continuous raster data, such as elevation datasets or imagery, you have to make a choice generally between nearest neighbor and cubic convolution, and decide whether it's important to preserve the original pixel values or to preserve the spatial arrangement.